Welcome back. So now that we described how symmetric encryption works, we are ready to move to asymmetric encryption. So all the crypto systems we discussed till now, as well as all of the other ones that we did not mention dating before the 70s, shared the common disadvantage that they are called symmetric crypto systems. Now, what do we mean by symmetric and what are some consequences? I guess that you already have something in your mind. Basically, symmetric crypto system simply means that both the encryption and decryption operations use the same secret key, and the ramification is that the key must be provided to both the sender and the receiver, in our case Alice and Bob, so that secure communication can take place. And of course, the keys must be kept out of reach from our malicious adversary Eve. Now, most experts had believed that there was no way around this symmetric key concept, and one of the main drawbacks of all symmetric crypto systems is the fact that in order for such a system to be deployed, the keys must be distributed to all participating entities before any secure communication can take place, which means that Alice and Bob, they need to first of all somehow establish, get access to the same symmetric key, to the same secret key, in order to use it to encrypt their communication. So such drawbacks can now be circumvented thanks to a remarkable revolution in cryptography known as public key cryptography or asymmetric key cryptography that occurred in the 70s. Now, the introduction of public key encryption marked a revolution in cryptography. Until that time, cryptographers had relied exclusively on shared secret keys to achieve private communication. Public key techniques, in contrast, enable parties to communicate privately without having agreed on any secret information in advance. And this is quite amazing result. To understand the importance of this discovery, imagine two people on opposite sides of a room who can only communicate by shouting to each other and have no initial secret. Now, with public key cryptography, they can talk in such a way that no one else in the room learns anything about what they are saying. So some highlights of asymmetric crypto. It's probably the most significant advance in the 3,000 years or more history of crypto. It uses two keys, a public one and a private one, and it's called asymmetric because the parties Alice and Bob are not equal. You remember in symmetric encryption, both Alice and Bob, they were using the same key to encrypt and decrypt messages. That's why it was called symmetric. In the asymmetric settings, you're using a public key to encrypt and a public key to encrypt and a private one to decrypt a message. Now, imagine that the public key is like your email address, right? So if you want to send me a message, if you want to email me, basically I need to give you my email address, which is publicly known. Okay, so I give you my email address and then you can send me an email. Now, I am the only one who can read that email because I'm the only one who has access to my email, which means that I'm the only one who have access to the password, to the login password, right? And this is like my private key. Now, these two keys, the public and the private, are linked in a mathematical way, but knowing the public key tells you nothing about the private one. Nevertheless, knowing the private key allows you to unlock information. Now, note that public encryption schemes are neither more secure than private ones. The security solely depends on the size of the key, and they cannot replace the private key encryption schemes. They are too slow to do that, and usually we use them, we combine them. Okay, so when we build a protocol or a service, we usually use both symmetric and asymmetric encryption. So imagine that we have Alice and Bob. So Alice on her end, locally, she generates a public-private key pair, and Bob, he's doing the same on his side, right? Then Alice is sending her public key to Bob. Okay, there's no need, let's say, to protect her public key. This is not entirely true, but anyway, for now, let's assume that there's no need to protect her public key. So she sends it to Bob. In any case, keep in mind that Bob knowing Alice's public key it doesn't affect Alice's confidentiality. Good. Now Bob will do exact the same thing. So he will contact Alice by sending her his public key. So a public key, which may be known by anybody, can be used to encrypt a message and to verify signatures. Today we will only talk about encryption and decryption. About signature we will talk in the next lecture. Now, on the other hand, a private key is known only to the recipient and is used to decrypt the message and sign messages, or which means create digital signatures. Now, why they call it asymmetric? Because basically those who encrypt messages or verify signatures cannot decrypt messages or create signatures. So Alice is using Bob's public key to encrypt the message M, but then she cannot decrypt it. Only Bob can decrypt it because he's the only one who has access to the corresponding private key that can decrypt that message. So a bit of history before we move on. So to achieve private communication without ever communicating over a private channel, a radically different approach is needed. Now, in 1976, two Stanford researchers, Diffie and Hellman, published a paper with the, let's say, innocent-looking title, New Directions in Cryptography. In that work, they observed that there is often asymmetry in the world. And in particular, there are certain actions that can be easily performed, but not easily reversed. So, for example, padlocks. Padlocks can be locked without a key, which is an easy operation, but then they cannot be reopened. More strikingly, it is easy to shatter a glass vase, but extremely difficult to put it back together again, right? Now, algorithmically, it is easy to multiply two large primes, but difficult to recover those primes from their product. Diffie and Hellman realized that such phenomena could be used to derive interactive protocols for secure key exchange that allow two parties, Alice and Bob, to share a secret key via communication over a public channel. This can be done by having the parties perform operations that they can reverse, but Eve, who is overhearing the communication channel between Alice and Bob, cannot. Although Diffie and Hellman did not provide a complete practical implementation of a public key crypto system, they provided an important key exchange protocol known as the Diffie-Hellman key exchange, by which two remote parties, Alice and Bob, could establish a secure key using public, which means insecure channels. Now, for their discovery, they were awarded with the Turing Award in 2015, and the Turing Award is often referred to as the Nobel Prize in Computer Science. So you can imagine that the importance, you can realize the importance of their discovery. And now in the photo here on the right, the one with the ponytail is, the long hair is Diffie, who was the PhD student at that point of Hellman on the left side of the photo. Now, inspired by the Diffie-Hellman paper and the need for a practical crypto system implementation of their concept, MIT scientists Rivert, Shamir, and Adelman invested the RSA crypto system 2 years later, in 1978. This has turned out to be one of the most important and widely used public key crypto systems, and for their ingenious achievement, they were awarded with the Turing Award in 2002. Good, so let's move on and describe how Diffie-Hellman works, right? So first, let's see the concept in a high level. So we have Alice and Bob, and what they want to do is basically to find a way where Alice will generate a secret key locally, almost on her own, okay? And Bob will do the same on his end, and at the end, they will end up generating the same secret key, which later will be used to encrypt any further communication, right? So in a high level, Alice and Bob derive a shared secret key over a public channel, no prior arrangements. So they publicly agree on two public values, P and G, okay, which means that they communicate in the beginning. Eve, who is in the middle and can listen all the communication between two friends, she can see the two public values P and G on which Alice and Bob agree upon, and then each one locally and independently chooses a private value. Alice chooses a random number A, and B generates another random number B. Now, then they both use clever mathematics to compute a shared secret key K. Now, Eve never overhears enough information to derive the shared secret, and this is the magic of diffie-hellman key exchange protocol. So let's see another example with colors, so that you understand better what's going on, I hope. So we have Alice, Bob, and Eve, and here the problem is how Alice and Bob can agree on a secret color without Eve finding it out. Now the trick is based on two facts. One, it's easy to mix colors together to make a third color. And two, given a mixed color, it's hard to reverse it in order to find the exact original colors. And this is the basis also for a lock. It's easy in one direction, lock, hard in the reverse direction, unlock it, for example, without a key. Now the solution works as follows. First, Alice and Bob, they agree publicly on a starting color. Let's say, for our example, yellow. In reality, they agree on two colors, okay, like P and G, as we mentioned in the previous slide. But just to make things simple here, let's assume that they agree on one single color, which is yellow. Then Alice and Bob both randomly select private colors. So Alice selects red and Bob blue, and mix them with a public color. Okay, so Alice mixes yellow with red, and this results in a new color, something like purple. And Bob is doing the same on his end, so he's mixing his private color blue with yellow with a public color, and he ends up with a masked color, like something like green, for our example, right? Now Alice keeps her color private, the red one, and sends to Bob the masked generated color. Bob is doing the same, so he's keeping his private color private, but he's contacting Alice by sending the masked color that he generated. Now notice that Eve, who is overhearing the communication between Alice and Bob, she has access to all public information, which is yellow, okay, the public color that they agreed in the beginning of the protocol, and the two masked colors that they were sent by Bob to Alice and Alice to Bob, right? Now the heart of the trick. So Alice and Bob, what they will do is that since after they receive the masked colors, they add their private colors to other person's mixture and arrive at the shared secret color. So Alice basically, she gets the green color that received from Bob, and he mixes that with his private color, which was red, and this will end up in a kind of purple color. Okay, Bob will do the same, so he will mix the pink color that received from Alice with his private color blue, and this will end up he will end up having the same color that Alice generated. Okay, and this is basically can be seen as the secret key that Alice and Bob will be using. The important thing now is that Eve will not be able to generate that color simply because she does not have access to the private colors generated by Alice and Bob. Okay, and therefore we achieve our goal, which is to frustrate Eve. Now, to do this with numbers, we need a numerical procedure which is easy in one direction and hard in the other. And this basically brings us to modular arithmetic. So let's see the mathematics of the protocol. Okay, it's very easy basically. So let P be a large prime number and G be an integer which is smaller than P. Now for every number n from 1 till P minus 1, G must have a power k such that n equals to G at the power of k mod P. Now solving the kth root mod P is considered but not yet proven, hard to do in polynomial time. Right? So we have Alice and Bob, Okay, now they start communicating and they agree on the two public values G and P, and then Alice on her end locally she chooses a secret integer randomly A. Okay, so she chooses A, she generates a random integer A, and then Bob, he's doing exactly the same thing on his end, so he generates a random integer B. Now Alice will calculate capital A, which is equal to G at the power of A mod P, and will send this public value to Bob. Bob will do exactly the same, but instead of using um, Alice's private value, he will use his own private value. So he will calculate capital B, which is equal to G at the power of B mod P. Now, here is a trick that they will do. Now, they both need to somehow, calculate the same shared secret key K, right? Now, to do so, Alice, that she's the only one who has access to her secret value A, she will calculate capital B at the power of A, and Bob, who is the only one who has access to his secret value B, he will calculate capital A at the power of B, and this basically will result to a shared secret key to the same key on both ends, K, which is equal to G at the power of AB mod P, right? So with this simple trick, both Alice and Bob, they managed to generate the same secret key, while Eve, who is in the middle and she is over here in the communication channel, she cannot find it because simply she does not have access to the secret values generated by Alice and Bob. So this was basically the diffie-hellman key exchange protocol. Now, some public key characteristics. So public key schemes utilize problems that are easy. We call them P-type, one way, but easy one way, but hard the other way. We call them NP-type. For example, exponentiation versus logs, multiplication versus factoring, etc. Now, traditional schemes like symmetric encryption schemes involve the sender putting a message in a box, unlocking it, sending it to the receiver, and somehow securely also sending them the key to unlock the box. Now, the radical advance in the public key schemes was to turn this around. So the receiver sends an unlocked box to the sender, who puts the message in a box and locks it. This is the easy procedure. And having it locked, it cannot get to the message. Now, and sends the locked box to the receiver, who can unlock it, also easy if the receiver has access to the corresponding key. Now, an attacker, Eve, would have to pick the lock on the box in order to access the message, and this is the hard part of the procedure. So the general algorithm is, again, we have the same scenario. Alice wishes to share a secret with Bob, so Alice basically she will use an encryption algorithm, which will take as input, of course, the secret message that Alice wishes to send to Bob, as well as Bob's public key, PK of B. Okay, so Alice has access to Bob's public key because it's public information. Everyone knows Bob's public key, so she can use it to encrypt her secret. Now, this encryption algorithm will output basically a ciphertext, which will be sent to Bob. Upon reception, Bob will give as input to the decryption algorithm the ciphertext that was generated and sent by Alice, as well as his secret key SK of B. And by doing this, the algorithm will output basically the secret. So Bob, by using the ciphertext generated by Alice and his secret key SK of B, he can recover Alice's secret. Now Eve, who is in the middle and she's overhearing the communication channel, she can get access to the ciphertext. However, she will be unable to find any valuable information regarding the exchange message, and that is because she does not have access to the secret, to Bob's secret key. Okay, one of the fundamental requirements of or hypothesis and way of asymmetric encryption is that Bob's secret key will never leave his perimeter. Okay, so always we must assume that our secret keys will remain secret. Okay, they will never be compromised. And thus we achieve again our goal, which is to frustrate Eve. Good. some definition, a semi-formal definition on asymmetric encryption. So a public encryption scheme is defined by a tuple of three algorithms: the generation algorithm, the encryption, and the decryption, such that generation is a probabilistic algorithm that takes as input a security parameter lambda and outputs a pair of public-private keys, PK, SK, PK for public key, SK for secret key. Now, encryption algorithm takes as input a public key PK and the message M and outputs a ciphertext C of M. Now, in contrast to the symmetric encryption, in asymmetric encryption, the encryption algorithm is also probabilistic. Now, finally, the decryption algorithm is a deterministic one and takes as input a secret key SK and the ciphertext C of M, and basically outputs a message M. So by giving to this algorithm as input a ciphertext and the secret key, we can recover the message. We said that the decryption algorithm is always a deterministic one. Now, we said that encryption in asymmetric encryption schemes is a probabilistic algorithm. So Alice, for example, she encrypts a message M with Bob's public key. This generates a ciphertext C of M, and she sends that to Bob. Now, after a while, let's assume that she decides to encrypt again the same message M with the same public key. This will generate another ciphertext of the same message. Okay, so by encrypting the same message with the same key, the output is different. And if she does this another time, again, we will have a different output. And if she does this 1 million times, we will have 1 million different outputs of the same message M. Okay, so this is important because in symmetric encryption, if Eve is looking at the exchange messages and Alice is always, for example, sending the same encrypted message to Bob, then Eve can understand that Alice sent, the same message twice or something like that. While in the asymmetric encryption setting, even if we just encrypt a bit, the ciphertext will be always different. Okay. It will look like a random result, a randomized result. Therefore, Eve will not be able to say if C of M is the same, represents the same message like the one was sent earlier by Alice. Now, so that's how basically how asymmetric encryption works. Now, glory forgone. Just one slide for two researchers that I think were quite important. So the concept of public key cryptography basically had actually been discovered by British cryptographer James Ellis in the late 60s, while the RSA implementation of it by Clifford Cox in 1973, while they were both employed at the Government Communications Headquarters, GCHQ, which is the British analog of United States NSA, secret agents. Now, the initial title that Ellis gave to his discovery while trying to solve the key distribution problem was non-secret encryption. Very nice title in my opinion. Now, the latter scientists did not receive any recognition for their discoveries until 1977, when the British government decided to declassify the information. Now, such stories are typical of many of the, let's say, unsung heroes of cutting-edge cryptography, who often are required by their governments to keep a tight lid on their discoveries as matters of national security. Yeah, so I guess everything in life is a matter of choices. Yeah, but I guess these two guys are really important, similar to diffie-hellman and the guys from RSA. That's what I believe. Thanks a lot. See you later. Bye.